Okay, following up on what we did in section 9.3 in the textbook, going through that in some detail, here is an outline in it in the PowerPoint format. Logarithmic functions, graphs of logarithmic functions, common logarithms, equivalent equations, and then solving certain logarithmic equations. Now, when we look at this right here, this is what we did in section 9.2, which was the function in exponential form, where our unknown x is the exponent. Now, when we did the graph of these, you may recall, this one looked like this a little bit. Did this pass the one-on-one horizontal line test? And it did. So we say this does have an inverse, and there's our one-to-one. Now, how can we find the inverse? Well, here is y equals, where we can substitute for the function symbol here, the y. And then now to find the inverse, we just reverse the positions. The y goes where the x is, and the x goes where the y is up here. Now, what is y? So this y here, the exponent to which we must raise 3 to get 8. To get x. And as I did in the textbook slides, I made this little picture. What is y? Again, y is an exponent to which we must raise 3, which is our base, to get x. Now, x is the result of raising 3 to a power, and what would that power be? In this case, it's going to be 3. So 3 to the third power is 27. So y over here is going to be a 3. It's this y will be 3. Now, when you put this up here, which is an exponential functional notation of an exponent, when we put it in its inverse form, remember this is read f inverse of x, that is the exponent to which we must raise 3 to get x. The exponent we must raise 3 to get x. And again, hopefully you're taking notes. We now define a new symbol to replace the words the exponent to which we must raise 3 to get x. And the symbol we're going to use for that is this right here. Log base 3 of x. One way to read it. I like it that way because that's what it says there. Another way is you can expand the word log into logarithm base 3 of x. And it means that. So here's an example. So the inverse of this would be log base 3 of 9 equals 2, And then how do you translate that? Well, remember, 3 is your base right here. And we're saying, what is the exponent? The exponent is what it equals to. And when you take the base 3, raise it to the second power, your results is 9. Because 2 is the exponent which we raised 3 to get 9. And again, you're going to have to look at some way to decode these. And hopefully what I'm offering here is a good method. Let's go on. So let's simplify these, and I'll set them up. Again, using this little method of displaying this, 3 is our base. It's going to equal 81 when it's raised to what power? Well, 3 to the 4th power is 81. So the log base 3 of 81 is 4. That's what we would put up here. So again, our base is 3. Our answer when we raise our base to a certain exponent is 1. So what would our exponent be? Well, in order for that to be true, the only value you could put there is a 0. So 3 to the 0 power is 1. So log base 3 of 1 equals 0. And for this one, our base is still 3. Our results would be 1/9 when we raise 3 to what power? And it would be 1/2. All right, let's see what they show us here. Okay. Again, I like the idea of setting it up in that little example form. And that's it there. Okay, graphs now of logarithmic functions. Well, this would give you an exponential function. And if you remember, what we're doing is getting the inverse of this, which is what we have down here. And we still have our x or y equals x, which is our axis of symmetry. And it would look like so. And notice they're doing something very similar here to what we have just described. And let's use that to solve some equations, or in this case. So here they're asking us to simplify this, where we have 5. Now the exponent is going to be this. And an interesting thing is that when it's in this form, that the log base 5 of 23, as it is the exponents to the 5, is raised to get 23. Raising 5 to that exponent, we then have the results of this equaling 23. It's important to remember that a logarithm is an exponent. Okay, so they're not like regular numbers they're exponents. So let's graph this. Now, remember, we didn't need the y initially. We're just going to do that, but setting it up in a graphing format, so to speak, you put the y there. You're going to do some points. We did a lot of these tables. So this is your regular exponential function. This is your line of symmetry. And then what do you notice about this? This, remember, is the inverse of this. So once again, if we fold along this axis of symmetry, we get a reflection. And I think all you need to recall here is that if you see a graph like this, you'll know that this did have its one-to-one values and therefore pass the horizontal line test so that it would have an inverse, and the inverse is the reflection of this. Okay. Now another common term or a useful thing in logarithms is the common logarithm. Now, base 10 logarithms are called common logarithms. They're useful because they have the same base as our commonly used decimal system. Our number system is a base 10 system. That is, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we get the 1, add a 0, and then we continue it. And there are, in a sense, 10 characters in our base. A 0, and then the 1 through 9 numbers. If you were to graph this using your graphing calculators, this is what this would look like. Now notice here this is x over 4, and then minus 2 kind of helps that your y-intercept, if there is something like that here, is going to be in the negative area. All right, equivalent equations. Here we use the definition of logarithms to rewrite a logarithmic equation as an equivalent exponential equation. Or another way around, if we have this, it's equivalent to this. So let's rewrite each as an equivalent exponential equation. Now for A, there is our equation. We'll get to B in a moment. So what we have then is for base 3, there's our base 3. Our answer is x, and our exponent is a negative m. So there's the equivalent equation to this. Now let's look at B. In B, we have this. Again, our base is A. Our exponent is 6, and that equals Z. All right, again, you're taking some notes on this to write this down, because as you have another example like this, you're able to follow the example. Okay, let's look at letter A here, and instead of going on, let me work it out for you. Now, 49 is what in relationship to 7? Can you all see it's going to be 7 to the second? So then, what does x equal? X will equal 2. Okay, now in letter B, it's a little different here because we're saying x is to the negative 2. This will equal 9, or I should say 3 here. Let's change that here. 3 to the negative 1/2. That's better. I had to take 9. Yeah. All right. So -2, -2. So what's our basis here? Our basis, x in this case, equals 3. Depending what unknown they want you to look for. Here it was an exponent. Here the x was a base. All right, let's see what they show us. Okay, and they're saying that this then is equivalent to this, which is okay, and this is equivalent to that. Okay, maybe I'm looking at this a little differently here. Oh yes, they've asked us to rewrite each as an equivalent logarithmic equation, not define the value of it. Well, okay, probably should have looked at this first here, but we showed you it works both ways. All right, solving certain logarithmic equations. Okay, let's take a look at number 1. And let me give it a try first. Okay, for these, what we're doing is looking for, again, a protocol, a strategy, a way to do it. Well, the key is this is our base, which we put here. This is our exponent, which we raise our base to, and then we don't know what x is. Well, what is 3 to the negative third? Well, it's going to be 1 over 3 to the third, which is 1 over 27, and that's what x equals. And in this one, your base is x. We're raising it to this exponent, and it's going to equal 4. So basically, we have x squared equals 4. And to do that, we take the square root of this from chapter 7, and plus or minus the square root of that. This will give us x equals plus or minus. I'm getting ahead of myself. Plus or minus 2. All right, let's take a look at it. Okay. Again, I don't like the way they write these fractions. I said that before. Again, you're putting it in this format. Again, there's your base. There's your exponent equals what? And when you solve it using the principle of square roots. Okay, and again, you're going to be practicing, and I strongly advise the practice before you do the quiz bee, and that way you'll get mastery. So we're saying, this is what we've illustrated a little bit, if you have your bases are the same, then your exponents equal one another. All right, that's a little bit of summary there. Okay, let's do this example. Now, this really helps when I have done the text already earlier today, and I kind of knew what was going on here. Otherwise, it needs to be interpreted. Well, using the idea of the previous slide, that if you have a to the, let's say, x equals a to the y, your bases are the same, then your exponents are going to equal each other. So here we had the base of 6, which I put right there. We knew the exponent was x. Now we had to convert our answer, which was 36, into some form of 6 as a base. So it's 6 to the second power. So what does x equal? X equals 2. And then here we had our base 9. T was our exponent. I didn't put that in my little box. And then I had to convert 1 to some item that's a value of 9. But what is 1? And it would be a 0. 9 to the 0 is 1. So here, T will equal 0 because this is a 1 once it's simplified. But that's these. Now let's see what they've done here. They did the same thing I did. Okay, good. Yep, yep, yep. Keep in mind as some hints here that the logarithm of base a of 1 is always going to be a 0 because anything to the 0 power is 1, as is the logarithm base a of a is always 1. That is, if it's the same value, because the first power of anything is always the number itself. Okay, a couple of little rules, and that winds us up.